In the vast, silent theater of the cosmos, we have long operated under a simple geometric assumption. Planets are spherical. Whether we are looking at marbles of rock and metal like our own Earth, or massive giants of gas and ice like Jupiter, gravity acts as the great leveler. It pulls everything inward, smoothing out the rough edges, resulting in celestial bodies that roll through the dark like perfect balls. But deep in the constellation Sculptor, roughly 2,000 light-years from Earth, the James Webb Space Telescope has just revealed a world that violently shatters this rule. Meet PSR J2322-2650b. This is a Jupiter-sized exoplanet that the universe has squeezed into the shape of a lemon. This discovery is not merely a quirky piece of space trivia to file away. It is what astrophysicists are calling a torture chamber of astrophysics. We are looking at a world orbiting a dead, rapidly spinning star at a proximity that defies logic, a world being stretched by gravitational tides so immense that they have deformed it into a prolate spheroid. Picture a cosmic rugby ball tumbling through a bath of high-energy radiation. Welcome to the Lemon Planet, a world where it rains diamonds, the year lasts less than a single work shift, and gravity is a sculptor working with a heavy, violent hand. To truly understand why this object exists, and why it looks the way it does, we have to look at the discovery itself. For decades, astronomers have hunted for exoplanets using the transit method, where they watch for a tiny dip in light as a planet passes in front of its star. But PSR J2322-2650b was not found around a normal star. It orbits a pulsar. A pulsar is the ultra-dense, city-sized corpse of a massive star that exploded in a supernova. These objects are nature's most precise clocks. They spin hundreds of times per second, blasting beams of radiation that sweep across the galaxy like a lighthouse. By timing these pulses with nanosecond precision, astronomers were able to detect tiny irregularities. Something was tugging on the pulsar. When the James Webb Space Telescope turned its gold-plated mirror toward this system in late 2025, it didn't just see a wobble. It resolved the thermal signature of a planet in distress. Most planets we know of, including Earth and Saturn, are what we call oblate spheroids. They are slightly wider at the equator due to the centrifugal force of their own spin. But this planet is different. It is being pulled outward at its poles, elongated toward its host star. If you could hold it in your hand, it wouldn't feel like a marble. It would feel distinctively like a lemon or an American football. The physics behind this distortion is a lesson in dancing on the edge of doom. To understand the shape, you must understand the monster it orbits. The host pulsar packs the entire mass of our Sun into a sphere only about 12 miles or 20 kilometers wide. The surface gravity on this star is billions of times stronger than Earth's. Now, imagine a planet the size of Jupiter orbiting this object at a suicidal distance of just 1 million miles. That is roughly 1% of the distance between Earth and the Sun. At this range, the gravitational differential is extreme. The side of the planet facing the pulsar is pulled significantly harder than the side facing away. This is the same tidal force mechanism that the Moon exerts on Earth to create ocean tides, but here, it is amplified to an apocalyptic scale. The pulsar's gravity is literally trying to rip the planet apart, while the planet's own gravity is barely holding it together. The result is that distinct, elongated lemon shape. Astronomers refer to this boundary as the Roche potential. The planet is filling its Roche lobe, a teardrop-shaped region of space where its own gravity dominates. If it gets any closer, even by a small margin, the lemon shape will stretch into a stream, and the planet will be spaghettified, dissolved into a ring of gas that feeds the pulsar. For now, it balances on the knife's edge, a football-shaped survivor in a gravitational hurricane. But the shape is only the beginning of the strangeness. If the geometry of PSR J2322-2650b is bizarre, its atmosphere is the stuff of science fiction nightmares. When the James Webb Space Telescope analyzed the light filtering through the planet's atmosphere using spectroscopy, the team expected to see the standard fingerprints of gas giants. They were looking for hydrogen, perhaps some methane or water vapor. Instead, they found a chemical composition that has never been seen before. The atmosphere is dominated by helium and carbon. There is almost no hydrogen, and absolutely no water. Dr. Michael Zhang, one of the lead researchers on the discovery, noted that it is a dry, scorched world, and the chemistry suggests this isn't a normal planet at all. The extreme temperatures on the planet reach nearly 3,700 degrees Fahrenheit, or 2,000 degrees Celsius on the day side. When you combine that heat with high pressure and a carbon-rich atmosphere, you get a terrifying weather system. High in the atmosphere, clouds of hot carbon soot float through helium skies. As this soot falls deeper into the planet's crushing interior, the pressure becomes great enough to crystallize the carbon. On the Lemon Planet, it doesn't rain water. It rains nanodiamonds. These diamonds likely fall toward the core, accumulating in a glittering, super-dense slush that might make up a significant portion of the planet's mass. It is essentially a treasure chest locked inside a radiation vault. This leads us to the question of origin. How does a planet made of helium and diamond end up shaped like a lemon around a dead star? The leading theory is a story of cosmic cannibalism, often referred to as the Black Widow scenario. Astronomers believe PSR J2322-2650b was not born as a planet. Billions of years ago, it was likely a star itself, perhaps a white dwarf or a small, sun-like star orbiting the pulsar. Over eons, the pulsar began to devour its mate. The pulsar's intense gravity stripped away the lighter hydrogen layers of the companion star, feeding on the material to spin itself up to incredible speeds. This is why millisecond pulsars are often called recycled pulsars. What we see today is the shriveled husk of that former star. The hydrogen is gone, eaten by the pulsar. All that remains is the helium-rich, carbon-dense core, now whittled down to the mass of Jupiter. It has been demoted from a star to a planetary oddity, trapped in an eternal, distorted dance with its destroyer. Life on the lemon planet would be impossible, but if we could safely observe it, the view would be spectacular. Because the orbit is so tight, a year, defined as one full revolution around the star, takes only 7.8 hours. The planet is tidally locked, meaning the nose of the lemon always points toward the pulsar. If you stood on that substellar point, assuming you didn't instantly vaporize, the pulsar would hang motionless in the sky, a blindingly bright point of blue-white light. However, the light wouldn't just be visible, you would be bathed in X-rays and gamma rays. The magnetic field of the pulsar would likely create auroras that don't just crown the poles but envelop the entire planet, glowing in electric purples and greens against the black soot clouds. Every few milliseconds, a lighthouse beam of radio energy would sweep over the planet. The noise in the radio spectrum would be deafening, a constant, rhythmic screaming of the star that powers the system. The discovery of the lemon planet is a watershed moment for planetary science for several reasons. First, it tests the material limits of planetary bodies. It asks the question, how much can a planet stretch before it snaps? This system provides a real-world laboratory for tidal physics that we cannot simulate on Earth. Second, it confirms exotic formation theories. It proves that planets can be formed through the destruction of stars, creating a new category of celestial objects known as ultra-low-mass white dwarf remnants masquerading as gas giants. And third, it presents atmospheric mysteries. The carbon-helium atmosphere challenges our models of opacity and heat transfer. How does a sky made of soot and helium distribute heat? The data from the James Webb Space Telescope will keep theorists busy for years trying to model these dynamics. PSR J2322-2650b is a testament to the resilience of matter. It has survived the supernova that created its host. It has survived billions of years of radiation blasting. It has survived being stripped of its outer layers. And now, it survives a gravitational tug-of-war that has warped its very shape. It is a lemon-shaped diamond in the rough, a distorted monument to the violence of the cosmos. As we continue to peer deeper into the universe, the lemon planet serves as a reminder that nature's imagination is far stranger and far more geometry-defying than our own.